You filled out course evaluations last time, so if you have questions now about anything that we are covering, why don't you just phone somebody who cares? I have no responsibilities left to you. No, that's not true. That's not true. We have spent some time talking about the issue of hypothesis testing, which is the fundamental issue in social science research, or in social research generally. And we've spent considerable time looking at one situation in which that takes place. That is a situation in which you're comparing a sample statistic with a population statistic, a sample mean with a population mean, or a sample proportion with a population proportion. What we're going to start discussing today is the last topic on the syllabus, hypothesis testing 2. And this is a situation in which you're comparing two sample means, X bar 1 and X bar 2. That is, you have two samples drawn from different populations, and you're comparing them for the same reasons we compared the single sample mean with the population, to see if they differ significantly, to see if one is significantly greater than the other, and so on. This is the classic research paradigm. This can be treatment control group. We could compare a group of females on some task, their performance on some task, with the average performance of a group of males on some task. We will in a moment go through the example, an example in the text, in which we're comparing the marital satisfaction of people without children with the marital satisfaction of people with children, couples with children. So this is the classic research paradigm. The classic research paradigm really being the treatment group, control group design. A group a system in which one group receives an explicit treatment and the other does not, and then their performance is subsequently measured. Let me ask, before we undertake this discussion, whether there are any questions that reflect back to the previous issue, and that is hypothesis testing 1, where we were comparing sample statistics with population parameters. Yes.
Like on the proportion, how do you know whether to subtract or to divide the two? Maybe I'm.
What's the two?
The percentages like this out of this or whatever, like the proportion.
We talked of proportional data being presented, and every time I say this, I have to say the same. Gozar goes through my head. The many forms of Gozar. We talked about proportional data being presented in any of three forms. The most common the most straightforward would be if proportional data were presented as proportional data. That is, if you were told that 0.50 of a group did something. That is rarely the case, though. You and I, in day-to-day life, don't invoke proportions very often in our conversations. We're more likely to talk about percentages, 50%. And if proportional data is presented as a percentage, you then have to transform that percentage into a proportion, and you do that by dividing by 100. You just put it on a different base. The third way in which proportional data can be presented is as frequency data. If we're told that 50 out of 100 did X, and again you must convert that to a proportion, and you do that by dividing the number of people who did X by the total number of people, which again is 0.50. Okay? Are there any other questions? Somebody said after class on Tuesday that they had looked at chapter 9 and it was very complicated. I'm going to reduce that. No, well, actually I'm not. I'm going to increase that complication and ambiguity so that this chapter will forever remain beyond your understanding. You filled out the teaching evaluations. What do I care anymore? This is my time. No, I will seek to reduce that complexity. Primarily in this way. If you recall in Chapter 8, when we were dealing with Hypothesis Testing 1, what we've labelled Hypothesis Testing 1, we were concerned with a variety of issues, including sample size. Because if sample size was large, we conducted a z-test, and if sample size was small, we conducted a t-test. And Healy raises that same criterion in Chapter 9. We will ignore it. We will ignore it. Regardless of sample size, we will conduct a t-test. So that's one simplification of Chapter 9. We will deal only with, we will examine all data by means of a t-test. If we go back to the basic need in this situation, you need two sample means. Let's assume that I'm interested in how much people like two candy bars. One is Snickers, the great candy bar of all time. And one is that charlatan of candy bars, the Mars bar. So what I want to do is have, you would agree, a series of scores under Snickers and a series of scores under Mars, and then I would compare the two. Would you agree? Yes? There are three ways of doing this, and we will look only at one of them, which is to simplify the chapter yet again. One way of achieving this outcome would be to randomly assign persons to one group or the other. That is, we'd have subject 1, subject 2, subject 3, subject 4, and so on to subject n-1 and subject n. This, if I pursued this strategy, I would take this group and simply randomly assign each of you to taste and evaluate either Snickers or Mars bars. And then I would go to each of you, and if you were in the Snickers group, I'd give you a Snickers bar or some portion of a Snickers bar. You would eat the Snickers bar, and then you would fill out some evaluation form of that, indicating how much you liked it. And if you were in the Mars group, I'd come to you with a Mars bar, and you do the same. Would you agree that in that instance, how much you like Snickers is unrelated to how much you like Mars bars? There's no connection between the two. And so you would conduct an uncorrelated t-test. You would conduct an uncorrelated t-test because the two sets of scores are uncorrelated. That is, they're independent of one another. Subject 1 is independent of subject 2. Subject 3 is independent of subject 2 and of subject 4, and so on and so on. Another way to go about this would be to have my Snickers group and my Mars group. But this time I come to each of you with a Snickers bar and a Mars bar. And I give...
I'm sorry, I must have missed it when you said it, but why does the Snickers group go down to S of n-1 and the Mars only go to S?
It goes to Sn.
How come the Snickers...
That's just to indicate, this is not S for Snickers, this is S for subject. This is just to indicate that you have different subjects in the two groups. So I have subject n-1 and subject number n. If there were 78 subjects, this would be subject number 77 and this would be subject number 78. That's all. That's all. That's just the notation simply indicates that you've taken some number of subjects and randomly assigned them to one group or the other. And you'll see the difference momentarily to other strategies. I could alternatively come to each of you with a Snickers bar and a Mars bar. And to half of you I'd give you the Snickers bar and you'd taste it and evaluate it, and then I'd give you the Mars bar and you'd taste it and evaluate it. And to the other half I'd give you the Mars bar first and the Snickers bar second, so that there was no order effect. But each of you would evaluate both the Mars bar and the Snickers bar. I would still end up, would you agree, with two sets of evaluations. One for the Snickers bar and one for the Mars bar. The difference is that subject 1 would appear in both groups, and subject 2 would appear in both groups, because everybody would evaluate both candy bars, down to subject n would appear in both groups. These data are not uncorrelated. In fact, they're correlated. They're correlated because those of you who like chocolate candy would probably evaluate both Snickers and Mars bars relatively high. Those of you who do not like chocolate candy would evaluate both candy bars relatively low. That is, the score given by subject 1 to the Snickers bar is not independent of the score that subject gives to the Mars bar. It's a function of the same individual with the same attributes, the same likes and dislikes, one of which is liking for candy. Yes?
You said we're only going to use one of these ways?
Don't worry about it. I'll get there. I'll get there. I'm obligated, however, to tell you the other ways. So this is a second possibility. The third possibility is that prior to having anybody taste any candy bar, I administer to all of you a test or a questionnaire that measures your liking for chocolate candy. And then I score your responses. And then I select people strategically. I select people with the same score. That is, the same liking for candy. So I take 2 of you who scored 10, and I randomly assign 1 to taste the Snickers and 1 to taste the Mars. I then take 2 other twins, one who scored a 14, another who scored a 14. I randomly assign 1 to the Snickers condition and 1 to the Mars condition. Would you agree that you still end up with 2 sets of scores? 1 for the Snickers, 1 for the Mars. Except in this situation, the data aren't uncorrelated either, because you've matched people strategically on the critical variable, so that you have subject 1A in the Snickers group and subject 1B in the Mars group. You have subject 2A in the Snickers group and 2B in the Mars group, and subject NA and NB. That is, the data are once again correlated because you've, as I've said, matched people strategically. You've measured a critical like or dislike regarding candy bars or chocolate candy, whatever it is, and then taken people who have the same liking for chocolate candy. These yoked pairs act as surrogate selves. That is, we're in essentially the same circumstance as we were in the second situation, where each of you would taste both the Snickers and the Mars bar. You act as your own control. Here you're yoked with a twin who has exactly the same level of liking for chocolate candy as you. Therefore, for the same reasons as were raised in situation 2, the data are correlated. We will not look at correlated data. We will examine only situations in which the data are uncorrelated because the persons in the study are independent of one another. First of all, then, just to summarize, I'm trying to simplify this chapter in 2 ways. One is, we will ignore the issue of sample size in this chapter and conduct all comparisons by means of a t-test. And second, we will look only at data that are uncorrelated. Okay? Are there any questions? Not that I care. Are there any questions? No? Let's go through an example of this then. This is my new teaching style. Rather than talk about these things in a vacuum, let's go through an example on page 217 of the text. Page 217. Application 9.1. An attitude scale measuring satisfaction with family life has been administered to a sample of married respondents. On this scale, higher scores indicate greater satisfaction. The sample has been divided into respondents with no children and respondents with at least one child, and means and standard deviations have been computed for both groups. Is there a significant difference in satisfaction with family life between these two groups? First of all, real life. The real life answer is, you betcha. This is just as an aside, because I teach family communication, all that stuff, you know. People get married, couples get married, and they live in absolute bliss for about 42 minutes. Maybe less if the Heineken didn't arrive. They live in bliss for some while. That is, typically people who marry, couples who marry, have high levels of relational satisfaction immediately after marriage. And that level of satisfaction tends to be relatively stable in most couples until the critical event, and that is the birth of the first child. And at that point, the relational satisfaction of both males and females dips precipitously. What we might say goes into the toilet. That sucking sound you hear is your relational satisfaction going down the toilet. This is especially true of women, and one can understand why. After all, they've been carrying this alien for 9 months. See, people say, you know, if men gave birth, you know, it would be different. It would for me. And it's not so much the pain thing, because I can't even get two there. It's this notion that something is growing inside of you. It reminds me too much of Alien. You know, you expect to look down one morning, you're having a shave, and suddenly something's just scything its way out of your stomach, and there's blood all over the bathroom, and you know it's not from your face. So I can't even get to the pain. But the woman has carried this alien thing growing inside of her for 9 months. Then comes a birth, which I understand is not really like going to a baseball game. There's no seventh inning stretch apparently, no popcorn, peanuts, cold beer. You know, it's pretty sterile and painful. After my wife had been in labour for 10 hours, and you know, as some of you do know, and as many of you will find out, they measure the intensity of the contraction. And there's this, at least when we went through it, there was this 100-point scale, and a needle just sweeps across there. And in Le Mans training, you're encouraged to convey that information to the woman. And so I was going, great, Kate, you know, this is like at 6 a.m. Great, you're up to 100. Well, it sort of stayed that way right through till 4:30 in the afternoon, and we weren't going anywhere. And at about 4:30, I had to go out into the waiting area and tell friends and family who were arriving from work the situation. Well, one of my sister-in-laws had bought me a poor boy from Antoine's. I used to eat those until I discovered how bad they are for us. Right. And so I literally must have inhaled that thing. It didn't take me any more than 3 seconds to eat this. And then I hurry back to my wife, who, when I'm 20 feet away, says in a voice that's not quite loving and encouraging, "You've been eating, haven't you?" And once a child is born, after that first ooh, ah, because when the first night my daughter was at home, there was a violent thunderstorm, and I woke up and I was concerned about her sleep and so on. I have to tell you, before you say, "Oh, that's nice of you," it was the only night I ever woke up. Not my fault. I just sleep soundly. I didn't fake sleep. You know, I didn't lay there, eyes closed, but really awake, waiting. No. But a child, a baby, just consumes your life, your energy, your time. You get to the end of the day and you think it's the end of the day, and then the baby starts up again. And my daughter would then, at about some hideous hour in the morning, 4 o'clock, climb out of her own bed and get into ours and lay on top of me and pull my eyelids open. Wait, Daddy. Wait, Daddy. So one shouldn't wonder that in the real world, relational satisfaction tends to dip a little when children come along. That's the bad news. The good news is that it does go up again as those children mature, stop giving you a heart attack, go out on their own, disappear for long parts of the day, which is reassuring. Then they get married and they have children of their own, and you just don't care at all. This is bliss. But the bad news is that you never again reach those halcyon days when you were newlyweds. That's true of, that's general data. It is not intended to describe and may not describe any individual here. But they will. So back to the problem. Who needs research to confirm this? We've already got the research we need. An attitude scale measuring satisfaction with family life has been administered to a sample of married respondents. On this scale, higher scores indicate greater satisfaction. So you understand what's been done. Somebody's generated a scale measuring marital satisfaction, and they've administered that scale, that is, they've given the scale to a group of married respondents who've replied to the items on the scale. The sample has been divided into respondents with no children and respondents with at least one child, and means and standard deviations have been computed for both groups. Is there a significant difference in satisfaction with family life between these two groups? And then you're given the the sample data for both groups. We have sample 1, which is the group with no children. Their score, their average score on this scale is 11.3. And the standard deviation of those scores is 0.6. And the number of people in this group, group 1, is 78. You then have the group with children. Their average score, this is group 2, their average score on scale is 10.8. The standard deviation of those scores is 0.5. And the number of people in this group is 93. As we pass along here, one observation. When you're dealing with uncorrelated data, well, let me go back, say it the other way. When you're dealing with correlated data, that by necessity, there are the same number of people in group 1 as in group 2, either because the same people appear in both groups, or because matched pairs appear in both groups. That is not the case necessarily with uncorrelated data. Here, there are 78 people in group 1, there are 93 in group 2. So there's no requirement that these two groups be of the same size. There is a requirement that this disparity in group size not be too large, because if it is, the problem becomes one of stability. That is, the means and standard deviations associated with the relatively larger group are more stable than are the means and standard deviations associated with the smaller group. And we encountered this at the beginning of the semester when we were computing standard deviations, and I talked about your GPA. When you computed your GPA at the end of your first semester, and then at the end of your second semester, there may have been a relatively large disparity because the number of scores you were dealing with is very small. By the time you've completed 120 hours here, your GPA is almost locked. Your performance in one course or in one semester, certainly in one course, will not change your GPA substantially at all. Because as those numbers become large, the statistics associated with the numbers, with the sample, become more stable. So that it's dysfunctional. Let me say this. While when you're dealing with uncorrelated data, it's not unusual to encounter groups of different size, it is dysfunctional when that difference becomes large, because the statistics associated with the large sample will be more stable than the statistics associated with the smaller sample. Having said that, here we are. Same three-step process. Step 1. We have to define the critical value of the test statistic T. What 3 pieces of information do you need in order to do that? Don't everybody rush at this one.
You need to know alpha and...
We need to know alpha.
Degrees of freedom.
We need to know the degrees of freedom.
And whether the test is one or two-tailed.
And the number of tails. Absolutely. Let's say alpha is 0.05. Should this test be one or two-tailed? Why do you say that? You said two-tailed?
I said two because the question indicates that there's no significant difference between the two, so it's not saying positive or negative. It's just saying there's no difference. Is there a difference?
Is there a difference? Yeah. Absolutely right. The critical sentence is there a significant difference in satisfaction with family life between these two groups? It does not say, are couples with no children significantly more satisfied? It doesn't say, are couples without children significantly less satisfied? It simply asks, is there a difference between these two groups? That is, the research hypothesis is that X bar 1 will differ significantly from X bar 2, so that the test should be two-tailed. Are there any questions about that? We now need to compute degrees of freedom. When we were dealing with one group and the population, degrees of freedom, you would agree, were given by n minus 1. Now you have to watch this trick. Would you agree that degrees of freedom were given by n minus 1? We could actually say n1 minus 1. The one group that we were dealing with. We have two groups here. So that degrees of freedom in this instance are given by n1 minus 1 plus n2 minus 1. You can rewrite this obviously as n1 minus 1 plus n2 minus 1, which equals n1 plus n2 minus 2. And because n1 plus n2 are the number of people in the study, you can rewrite this as n minus 2. In general, the degrees of freedom in a t-test are given by n minus k, where k is the number of groups. So when, in the first situation we looked at where there was a single sample, k was equal to 1, so that degrees of freedom were given by n minus 1. Here there are two samples, so k is equal to 2, so the degrees of freedom are n minus 2. However, each of these statements says the same thing. And you can compute degrees of freedom from whichever you like. Okay. But you should pick one of them, and it seems to me that this is the least likely. But certainly you can pick any of the others and easily compute degrees of freedom. But you should settle on one prior to the exam, prior to going through any examples by yourself, and consistently compute degrees of freedom in that way. So in this instance, we have 78 people in group 1, we have 93 people in group 2. That's a total of 171, yes? So n, the number of people in the study, would be 171. So the degrees of freedom here are, would you agree, 169? Yes? 171 minus 2. You now go to Appendix B with alpha equal to 0.05, a two-tailed test, and 169 degrees of freedom. And if you do that, you discover that the critical value of T is plus and minus 1.98. Actually, if you go to Appendix B, you will find that there is no row associated with 169 degrees of freedom. And you therefore have to make a choice between 120 and an infinite number of degrees of freedom, and you choose 120 because it generates a higher critical value. Having said that, that will not be a problem on the exam. That will not be a problem on the exam. The degrees of freedom that you need will be in the table. Okay. But we've defined a critical value of T. We now have to compute the observed or obtained value of T. And to do this, we invoke the following formula. It equals x bar 1 minus x bar 2 divided by the square root of S1 squared divided by N1 minus 1 plus S2 squared divided by N2 minus 1. This is straightforward. This is straightforward. I think there's nothing very complex about this. But what you should be sensitive to, the descriptive statistics you're given include standard deviations. Would you agree? You're given S, the standard deviation. And you're given S because S is expressed in the same units as X bar. We talked about this when we computed variance and standard deviation. Variance is expressed in squared units, xi minus x bar squared. Standard deviation, which is the square root of variance, is then expressed in the same units as the mean. So you're given, and you will be given on the exam, means, standard deviations, and the sample sizes. What you are required to do here is include variance scores. That is, you have to square those standard deviation scores. So that in the current example, we have x bar 1, which is 11.3, minus x bar 2, which is 10.8, divided by the square root of S1, which is 0.6 squared, divided by N1 minus 1. N1 is 78, so N1 minus 1 is 77, plus S2 squared, and S2 is 0.5, so S2 squared is 0.5 squared, divided by N2 minus 1. N2 is 93, so N2 minus 1 is 92. Are there any questions at all about the general formula for T observed, or moving from that general formula to this specific instance? Yes.
How do you decide which no children or with children is X bar 1 and X bar 2?
That's a good question. It's arbitrary. It's arbitrary. But once you have decided which is X bar, which is group 1 and which is group 2, You simply have to follow that all the way through. So that if you had decided that couples with no children were sample 2, then those scores would be X bar 2, S2, and N2. Typically, this is not an issue on the exam. It's not an issue on the exam. I haven't played a trick where I've labeled something group 1 and led you to label it group 2 so that I have two the same scores, only 1 plus and 1 minus. You see what I'm saying? I don't have there will be no questions in which the observed value of t is, let's say, plus 3.11 minus 3.11. You simply, having made that decision, have to follow it, the implications all the way through to retain consistency. Are there any other questions? I have not performed this computation, but Healy has, and Healy says, according to Healy, the observed score here is plus 5.56. So you have T critical of plus and minus 1.98 and T observed of plus 5.56. We now need to evaluate the null hypothesis, and we're once again in this situation. Can I just go through this? We have at the center of this distribution, we're now dealing not with single scores but with different scores. X bar 1 minus X bar 2. So at the center of this distribution is mu, which is equal to X bar 1 minus X bar 2 equals 0. That is no difference between the two means. We have established critical regions. The boundaries are 1.98 standard deviations below the mean and 1.98 standard deviations above the mean. We've isolated 95% of all of the scores. And if our specific difference between the two means, once placed in this distribution, is in this striped region, we will fail to reject the null hypothesis. We are again in search of Denzel Washington, Brad Pitt, Sean Connery, or the Elephant Man, Quasimodo, and the guy who's in my 5th grade class with head like a balloon and eyes all over the place. This particular difference mean difference is 5.56 standard deviations above the mean. It is somewhere out here. Would you agree that it's a rare event? It is distantly removed from the center of this distribution. You would therefore fail to reject the null hypothesis. Would you agree? God, I hope you don't agree. No. I hope you're saying, what? What? You would therefore reject the null hypothesis. You're 5.5 standard deviations removed from the mean. You are a freak. You're not just unusual. People look at you and their eyes pop out. People approach you and you can hear them telling their children, don't look, your eyes will pop out. You reject the null hypothesis. You conclude that there is a significant difference in the level of satisfaction between couples with no children and couples with children. Are there any questions? Yes.
I don't understand how, I know you didn't compute it, but I computed it and it doesn't equal 5 points, whatever.
What did you get?
Like one step away. I did it once already, I'm doing it.
Okay, it's alright. It's alright. Healy is sometimes wrong. What you should do is outside of class, go through it and see if you can come anywhere near Healy. You got what?
It says...
Error?
No. 1528. 5.
I don't think that's right.
Yeah, I don't think it's right either. I don't know how... But
The way to do this is, let's see, parentheses, 0.6 squared, parentheses, divided by 77 equals plus parentheses 0.5 squared let's see I think divided by 92 equals, although I'm not sure now as I do it whether this goes inside. But anyway, you then have some number. You then hit 1 over x. You invert that number. Actually, sorry, first you take the square root of that score. Which equals, and then you invert that score, multiply it by parentheses 11.3 minus 10.8 equals, and you should have the answer. But it doesn't matter. However you work through this, you don't have to use this. You can do 0.6 squared divided by 77, take it out, write it down. Then you can put 0.5 squared divided by 92 and add the 0.6 squared divided by 77 back in, take the square root, write that down, and move through. Do this in a way that that is comfortable to you, and do it in the same way every time.
I did it again. I got 5.82, which is closer, but it's still wrong.
It's a lot closer. It's a lot closer. I will do it on my trusty 22-year-old calculator, and see what I get. No, I can't use those newfangled things. I really can't. I really prefer a quill and a bottle of ink, you know. Well, I graduated to the slide rule, but I'll go back to the abacus, sure. What I advise you to do is first of all to work through some of the problems at the back of the chapter. Second, I will load onto WebCT assignment 7, which will be problems of this sort. Okay, I will also load onto WebCT either today or tomorrow the answers to assignment 6, even though I went over that in class. But the more practice you get at these, the easier they will become. And as I recall, we're a week away from the third exam. Yeah. But after that, it's all over. Well, I don't mean that in the bad way. I mean that in a good way. Yes.
Could you put that paper back up that shows how to put it in the calculator?
Why don't you just take it afterwards? Okay. And I'm not absolutely sure that that's it, but well, I'm really not. You can just try it. It's with the calculator in front of me. I could tell you, but holding some things in my head for some reason is not straightforward. I will load onto WebCT some sample problems of this kind. The last exam is a week away. You should have had ample rehearsal at hypothesis testing 1. That is, situations in which you're comparing a sample statistic with a population parameter. That leaves only hypothesis testing 2, the circumstance in which you're comparing two sample means. We've been through an example of that this morning. They all work the same way. If I talk about assignment 6 and that type of question and how it will appear on the exam, each of the questions on assignment 6 required that you provide 3 pieces of information. The critical value of the test statistic, the obtained or observed value, and then you had to evaluate the null hypothesis. As I indicated in here before, you will see the same on the exam, except they will be separated into three questions. The first will give you the scenario and say if alpha is 0.01, the critical value of the test statistic is, and you will have a choice. The second question will say in regard to question 1, what is the obtained or observed value of the test statistic, and you will be given choices. And then the third question will be in regard to question 1, you would A, reject the null hypothesis, B, fail to reject the null hypothesis. My point is, if you stack 6 or 7 of those questions together, you got 21, 16, 18 or 21 questions. You got a substantial part of the exam accounted for. Somebody asked me in the earlier section of this course how much time you will have. It's an irrelevant question, because I'll give you time. I will give you 60 minutes or 65 minutes or 70 minutes, but everybody gets the same amount of time. You walk in to take the LSAT, you don't go up to the proctor afterwards and say, you know, I could have done better on this exam if I'd have had more time, because they will just walk straight on by. People who say I could have done better had I had more time, my response is you didn't know the material well enough. And I honestly believe that to be true. There is no reason to be disturbed by this. When you think about those questions that were on assignment 6 and will be back on the exam, 2 of the 3 in the set require minimal time at all. One determining the critical value of the test statistic, and the other evaluating the null hypothesis. The time-consuming part is computing the obtained or observed value of the test statistic. You should have by now found a way of doing that with which you're comfortable. A system in which you're well rehearsed. And I advise you to do the same in regard to problems of the sort that we covered today. Another question I was asked earlier this morning was, how many word questions will be on the last exam? I don't know. But it's quite obvious that most of the questions, in fact, clearly the vast majority of questions, will be of the kind that we've dealt with this morning. We've spent almost all of our time doing that. I've made comments along the way, as I did this morning, about sample size and the stability of the statistics and so on. But for the most part, we have been computing, defining obtained values of a test statistic, computing observed values, or defining critical values, computing observed values, and evaluating a null hypothesis. And that's what the third exam is going to look like. Are there any questions? Yes.
From Chapter 9, from what we're given in the syllabus to read, since we've cut out a lot of certain things that we don't need to know, do you still want us to know that because we're assigned to read that, or just kind of...
The readings have always been assigned on the basis that I believe they help your understanding. If they don't do that, you should stop reading. I think it's fair to say that there have been no questions on the exam over topics that we haven't discussed in class. So that the critical thing is, have we discussed the issue in class? And if you've understood the discussion in class, and if you have notes that help you retain that understanding, and if reading Healy complicates the issue for you, I would rely on your class notes. Are there any other questions? Let me just say then, have a good Easter, drive carefully. I'd like to see you all back here after Easter, and I'll see you next Tuesday.